um, if I remember correctly, this is chapter 6, okay, the point location, okay, knowing where you are, okay. So this is like it's remember like in the last chapter, we talked about the range search, right? In the range search, we are given a number of points and a range, okay, a query range, and we are asked to return the point in a given range, okay, quickly, efficiently, okay. So that's the range search, okay. So this one is also a query, but it's also like a kind of like a special query, but it's different, okay. It's different, okay. It's like for instance, okay. Say you are you locate a particular point on your map, and you would like to know like which country this point belongs to, okay. So for instance, okay, so this is of course a very common application, right? So you know, like we could have a map that represent like for the region of each country, right? For each country we have a different region, okay? That's basically a subdivision, right? We talk about subdivision, right? So this problem basically is like to ask, okay, given a map or a subdivision, okay, we want to find a point, okay, and we want to, and given a point, of course, we want to find which face contains that given point efficiently, okay? So that's like the problem basically, okay? So, and for the subdivision, how the data structure that stores a subdivision is called the doubly connected linked list, H-list, I'm sorry, doubly connected H-list that we have talked about in chapter 2, right? So, so here, okay, it's basically that data structure, okay, that data structure, but with a little bit different, okay. We try to only use those ages, okay. We try to only use those ages, okay. So how do we get this job done efficiently? Let's try to think, okay. Intuitive. If you want to solve this problem, okay, if you want to solve this problem, okay, say this is a subdivision, right? You can treat this subdivision as a number of line segments, okay, as number of line segments. Each of these is a line segment, okay, and then, okay, because we would like to answer which region contain that given point efficiently, okay. So, well, a straightforward thinking is like this. We can sort of like draw a vertical line that pass through each point here, each endpoint of this segment, okay. So it will result in something like this, right? It will result in something like this, right? Okay. And Well, once we divide the space into a number of these vertical subspaces, okay, if you know the x-coordinate of the point, you can quickly find out which this long subspace contain that point, right? Right? Okay, say like, okay, now, okay, this is like a -5, this is -3, this is 0, 3, 5, 6, and so on. Okay, so if your point is has an x value 2, then you know it's in between 0 and 3, right? That can be obtained very quickly, right? Okay, so one simple way to do it is you just scan, like from left to right, right? From left to right, and then find the appropriate, find the region, okay, or like the range of the x that, for one such a subspace that contain the x-coordinate of the given point, right? Okay, so this is like a very simple approach. However, okay, this approach, if you scan from the left to right, okay, it's basically a linear. It takes linear time, right? So if you want to get this job done a little bit more efficiently, what you can do is you can sort of like put them, okay, because each of these, okay, actually in the textbook, okay, we call each of these long strip as a slab, S-L-A-B, slab, okay. So each of these slabs, okay, because these slabs actually they have like a left and the right relation, right? They have left and right relationship, right? So since they can be ordered from left to right, so we can put them, okay, in a binary search tree, right? We can put them in a binary search tree. And then with such a binary search tree, okay, so the basic idea is like we try to first check, okay, if this point is like inside here, okay, if it's inside here, great, we're done. Okay, if not, if it's on left, we go to this subtree, the left subtree. If not, we go to right subtree. Okay, the point is above, is larger than this region. We go to right subtree and so on. Okay, so that's the basic idea. Okay, so if you do it, do like this search this way. Okay, then okay, locating the slab that contain that point takes log n this much time, right? Takes log n much time. Okay, assuming you have n number of slabs. Okay, so locating a particular slab that contains the given point takes log n. Okay, but once you get to that slab, what do? Okay, the slab looks something like this, right? The slab always looks something like this. Okay, so similar to the relationship between different slabs. Okay, if you look closer to a particular slab, okay, it is also broken into a number of subspaces, right? And this number of subspaces, they also have relationship, right? Either below or above, right? Either below or above. Okay, so if it's so using this kind of idea, okay, you can also check. You can also order this put this like a subspaces, okay, into a binary search tree. Okay, so that like when you're given a point, okay, you first check if that point is in here, in the middle one. If not, if it's lower than this one, you go to the left subtree. If it's above this region, okay, you go to the right subtree and so on. Okay, so by assuming you have n, again, assuming you have n such subspaces, okay, then okay, the search, okay, to locate which of this this small area that contain P only takes, okay, well, log n amount of time, right? So this one takes log n amount of time, this one takes log n amount of time, and once you are able to identify, okay, the point is located, okay, say like in here, your job is pretty much done, right? Okay, so this is an intuitive approach, and it works fine, okay, it works great, okay? So, of course, there are some details to theory. For example, okay, how do, okay, for a given point, okay, how to check if this point is above, is inside a region or not? Basically, you need to check, okay, if the point is above a line or below, above this line segment or below this line segment. Okay, basically it's like this. Okay, checking a point is above a line segment or below a line segment. Well, this thing you should be able to do this like using like a high school math, right? Okay. If you don't know how to do it, okay, I mean we could certainly talk about it after the class, okay, because this is really like a high school math. It's not even calculus, right? It's like a geometry, not computational geometry, like high school geometry stuff. Okay, okay. So because you are given the coordinate of these 2 points, you are given the well, actually not coordinate of these 2 points, because you know, for example, this is this line segment belong to, for example, okay, assume this is this one. So this line segment belong to this one, right, from here to here. So you know these 2 points, okay, and you know like the given point, okay. So by using these 2 points and the given point, you know you can identify whether this point is above the line segment or below, or even on that line segment. Okay, so that's like a trivial calculus, which calculation which only take constant time. Okay, take constant time. So if it's below, so you know you need to go to the left subtree, right? If it's above, then you need to check if that point is above this line or not. If it's below, if it's above this line, below this line, great, it's inside here. If it's also above this line, so you need to go to right subtree and so on. Okay, so that's like pretty straightforward. Okay, those are the detail that I need to fill in. But basically, okay, so this idea, the search time, the time to do the search, okay, is big O log n. Okay, even in the worst case, okay, the time complexity for queries big O log n, because they are just 2 log n. That's it. Okay. Assuming you are given n line segment, assuming you are given n line segment, okay, such time complexity is big O log n. Okay, the query. But how about storage complexity? Storage complexity. Well, for each of these slab, okay, for all these slab, we need to have a binary search tree, right? And for each slab, we need to maintain another binary search tree, right? So let's look at the worst case scenario. Worst case scenario, okay? Here, okay, we have roughly n over 4, okay, n over 4, this many straight lines, okay, well, actually n over 4 minus 1, okay, and also this one is like, we have n over 4, like this small line segment like this, okay, so the total will be how many line segments? Huh? Because we have n over 4 small line segment. We have n over 4 this line segment. So totally how many? N over 4 plus n over 4, right? Huh? You guys don't know n over 4 plus n over 4? N over 4 plus n over 4. Somebody tell me, please. You guys are in graduate school, computer science graduate school. Nobody can tell me this? N over 2, right? Okay. This many line segments, right? Okay. I hope this is not a difficult question for you guys. Is it? Okay. So if you consider the including, okay, the points as well into the complexity calculus calculation, okay, we have n over 4, this many small points here. We have n over 4, this many small points here, right? And we have we have n over 4, this small line segment. So totally, it's roughly n over 4, right? Okay, because they are consecutive line segments. So each of these is shared by 2 line segments. So totally, about n over 4 plus n over 4 plus n over 4, roughly 3n over 4, right? Right? This is number of vertices. This is number of segments. Right? 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 So there, no matter how you calculate it, okay, if you calculate only the segments, okay, it's a linear to n, right? It's linear to n. If you calculate, if your calculation of complexity includes the segment and the vertices, then the total number will still be linear to n, right? Will still be linear to n, right? Okay, so you have linear number, you have n approximately, okay, big O number complexity of your subdivision, okay. But if you use like the idea that we just talked about, okay. So think about this. For this, for the binary search tree that that take care of this slab relationship, what is the size of that? We have n over 4, this many slabs, right? Okay, we have n over 4, this many slabs. So if you want to create a binary search tree with this many leaf nodes, what is the amount of space required here? Binary search tree. Nobody can answer? This is supposed to be the fourth class, right? Fourth class into this semester. How many times we have talked about binary search tree? The only time, the only lecture we didn't talk about binary search tree is the first one, right? Right? So binary search tree, we have talked about binary search tree many times, okay? So if you have a number of leaf nodes, what is the total number of space, storage space required for the binary search tree? Nobody know? We have a big problem. Okay. I think I strongly suggest you guys to study the property of a binary search tree. Okay. For this class, because this is supposed to be like one of the data structure discussed in the data structure class, not algorithm class, data structure class. Okay? Okay, which should be covered in your for sophomore year. Okay, at least 3 years ago, right? 2 to 3 years ago, depending on how quickly you finish your college. Okay? If you have a number of leaf nodes, the non-leaf nodes is bounded by, if it's a binary search tree, non-leaf nodes is bounded by n. Okay? So the total number of storage will be bounded by 2n. Okay? You can draw a very simple example. If you have 2 leaf nodes, how many internal nodes do you have? 1. Right? Right? So it's 2 minus 1, right? 2 minus 1, right? 1 plus 1 is 2, right? Minus 1 is 1. Okay? And if you have 4, leaf nodes, how many non-leaf nodes do we have? 3. 1, 2, 3, 4. 4 minus 1 is 3, right? Okay? Any question for this? So if you have if you have this many n over 4 slab as your leaf nodes, what is the size of your binary search tree? Somebody tell me. It's bounded by how much? Huh?
2 times n over 4.
Great, great. We finally have someone who knows math. Great. Okay, so the result will be what?
2n bits.
N over 2, right?
Yes.
N over 2. Right? Is it very difficult? I hope not. I hope not. If it is, I don't know if it's because of the English or it's because of the math or because of the data structure. I don't know. Okay, you guys have to tell me. Okay, you guys have to tell me. We have some problem. We have some problem. This is supposed to be very easy. Okay, it's supposed to be very easy. Okay, so, well, great. So this binary search tree is linear, right? It's linear. But look at each slab because for each slab, how many of these subspaces do we have? Roughly. I'm not asking for a very accurate number. Because we have roughly this many n over 4 like line segments, right? So this subspace is approximately n over 4. Is that right? Is that right? Is that right? To be more accurate, you can say, oh, it's n over 4 minus 1. Right? Okay, but roughly n over 4, right? In terms of order, it's not an issue, right? Okay, it's n over 4. Okay? So for this slab, as I said, okay, you need a binary search tree, additional binary search tree, to be able to identify the point belong to which subspace here, right? Okay, so that binary search tree, what is the size?啊？
刚刚那个问题的中文是什么意思？
这个 slab， 它分成n 这么多个那个小格子，对不对？小格子，那我们需要一个 binary search tree， 能够让我们那个搜寻，对不对？好，那我现在问你，这个 binary search tree 它的大小是多少？对啊，n嘛，对啊，大概n，对不对 ？The problem is exactly like what I just asked, right? For this one, right? Okay, so the space required for this lab, okay, is about n over 2, right? So how many slabs do we have? N over 4. So total will be n over 2 times n over 4, right? So it's going to be n squared over 8, right? Okay, so that's why, okay, the storage complexity is this one. Okay? So this is we are given a particular example. This is an example that, okay, if we use the previous, this straightforward idea, yeah, I mean, the worst case scenario, yeah, we are going to end up with this many storage complexity. The storage complexity is going to be n squared, okay? The worst case scenario. Okay? So, well, so this solution, okay, the query time is pretty nice. Okay, in the worst case scenario, it is still a log n, because just take log n to find which slab that point belongs to, and takes like a log n to find like a small space. Okay, that point belongs to. Okay, so it's two log n basically, 2 log n calculations. So the order is log n, no matter how you consider it. Okay, but the complexity of the storage is n squared. So this solution, okay, if it is used for your desktop computer, it's great, no problem. As I already told you guys, like a desktop computer, the storage is cheap, right? The storage is cheap. So this solution is not a problem for desktop computer or for any computer which does not have memory issue. Okay. However, if you want to use this solution for the embedded system, you may have some problem, right? Because it's going to take too much memory, right? It's going to take too much memory. Okay? So, what we are trying to seek now is, can we have a better solution? Okay? When I say better solution, what I'm talking about is, we want to have a cheaper storage complexity. Cheaper storage complexity. We do not want to sacrifice our query too much. So at least, on average, or for the expected query complexity, I want it to stay to be log n. Okay? The worst case, of course, I probably cannot. I have to sacrifice a little bit. Okay, but at least the expected query complexity, I want to be as good as log n. Okay, so that's the problem this chapter is dealing with. Okay. So along the same logic, okay, we are still trying to, for each endpoint of this line segment, we are still trying to, draw a vertical line. Okay, so this idea, okay, is pretty much the same as the intuitive idea that we just talked about here. Okay, with one little twist. What twist? When this line, for example, when we draw this straight line, okay, vertical line, when this line meets another line segment, it will stop. It will stop. Why? Because we do not want to cut, the space too many. We do not want to have too many subspaces. Okay, because each subspace eventually is going to require some storage space, right? So the idea is we just do not want to have so many subspaces. So the idea, okay, we try to draw a vertical line for each endpoint. This idea is still there, but it's just like we try to put a limitation. There are some additional things I would like to mention. Okay, first, okay, we assume there's a bounding box for our subdivision. Okay, so this bounding box is a very simple rectangle. Okay, rectangle that basically enclose the whole map inside it. Okay. So in this, for example, in this figure, the bounding box is represented by this dotted line. Okay. And in addition to that, we have two assumptions. Okay, we have two assumptions. The first assumption is we assume, okay, the line segments do not cross each other. Okay, so for example, okay, you don't have two line segments. You have like something like this. This is line segment, and you have another line segment, something like this. And this one is not a vertex. Okay. We don't have we assume, okay, such a segment crossing. We assume such segment crossing is not allowed. This is okay. This is okay. Why? Because all these line segments will be obtained from the doubly connected edge list, right? Okay. So in the doubly connected edge list, if you have such scenario, this point is going to become a vertex, right? This point is going to become a vertex. And the half edge is going to be broken. Remember, it will be separated into two half edges, right? So, because we don't get the segments from anywhere, okay, we get those segment information from the doubly connected edge list. So this crossing, okay, apparently they will be broken. Okay, if there's a crossing, okay, the line segment will be broken into like appropriate pieces, such that okay, that intersection will no longer be there, or it will be considered as a vertex. Okay, it will be considered as a vertex. So this assumption number one is fine. Okay, we don't, you know, in the reality when we process, when we do this, when we try to solve this problem, okay, because the map information is obtained from our data structure, which does not have the closing anyway. Okay, but the second one is a little bit special. Okay, the second one is a little bit special. Okay, we assume no two distinct endpoints, okay, of segments in S have the same x coordinate. Okay, so we do not assume. Okay, we assume there's no two endpoints having the same x coordinate. This is special. This is special. Okay, okay. We call such assumption as general position. General position. Okay. So this general position apparently is not realistic, right? It's not realistic. Of course, you could have a map with like such that the endpoints share the same x coordinate value. That's not an issue, right? For regular map, right? So don't worry about it. Okay, we have this assumption just to simplify our discussion, because later on, I'm going to talk about how we can relax this assumption. Okay, I'm going to talk about how we can relax the assumption such that our solution is able to handle this type of stuff. Okay, so don't worry about it. So it's kind of like what we had in the previous chapter. Remember, in the previous chapter, we assumed no two points have the same x coordinate or y coordinate, right? That's a very strong assumption, remember? Okay, in the previous chapter, okay, when we talk about the general solution, okay, this is just part of the half of the assumption that we used in the previous chapter. But in the range search, remember, range query, okay, range query, and later we use like a composite number, okay, to relax that assumption. Okay, if you still remember, or if you forget about it, fine, check out the slides. Okay, we talk about that, and I promise you that will be like one of the homework problems. Remember, okay. But anyway, okay. So this one, okay, this one is still unrealistic. We are going to relax this assumption later. Okay. So once you use this method to break your space, okay, interestingly, you are going to find that all the this small area that you end up with, okay, they are trapezoids. What is trapezoid? Again, I mean, you probably don't know about this term, but you know this term, math term, from your elementary school. Okay, 梯形. Don't tell me you didn't know about 梯形. I mean, you don't know 梯形 in your elementary school, right? Right? What is the definition of 梯形 trapezoid? Yeah. Okay. 四边形，有两条线是平行的。Okay. Right? Okay. Because we are going to, extend the vertical lines. So you are going to find, for example, like this one. Okay. Apparently, like the left side and right side. Okay, because they are like vertical lines, so they are in parallel, right? Same thing here. This is a trapezoid because the left side and right side, they are parallel, right? But you may also find some, exceptions. For example, like, well, you may ask, how about this one? This is a triangle, right? This is not a trapezoid, right? Okay. The explanation I have for you is that, okay, you can sort of consider the triangle as the degenerated trapezoid, okay, when one of the edge, one side, okay, is shrinking into a point, okay, this part, okay, left side, okay, is shrinking into a point. In that case, it becomes a triangle. Okay? So if you consider triangle as a special trapezoid, yeah, I mean, so everything here will be trapezoid. Okay? Everything here will be trapezoid, including this one. This one you can say, oh, this one is a rectangular. Okay, but rectangular, of course, is an example of trapezoid, right? Okay, in elementary school, they will ask you like, okay, they give you some shape, and they want to ask you like, which one is rectangular, which one is trapezoid, which one is blah blah blah, right? And then apparently, the rectangular will be considered, okay, will be classified as both, rectangular and trapezoid, right? No problem about that, right? Okay. So, okay, let me finish this one before we take a break. Okay, let's take a closer look of a trapezoid here. Okay, so this is one of the trapezoid. Okay, you will find that, of course, when we talk about trapezoid, okay, in this figure, okay, the trapezoid always have four sides. Okay, of course, I mean, if it's like a triangle, one of the side is shrinking into a point, right? But basically, okay, you could consider four sides. There are four sides, okay? At the left side and the right side, they will be contributed by 1 point, because it's because of the point. This point, you draw a vertical line, right? And this one is this point. You draw a vertical line. So these 2 points, okay, one contribute the left side, one contribute the right side. Okay, so the left side and the right side are of a trapezoid here are always contributed by the point. Okay, so we call the left side and right side as like left P, right P. Okay, trapezoid we use this delta to refer to it. Okay. If you ask me why do we use delta, okay, delta looks like a triangle. It doesn't look like a trapezoid, right? Okay, it's because, okay, well, if you check out the PowerPoint slides, okay, you don't see a trapezoid symbol there. There's never a trapezoid symbol, okay? So the textbook has to use like a triangle. But you get an idea. This one is actually a trapezoid. Okay, this is not a triangle. Okay. But the top and the bottom, they are of a trapezoid. They are contributed by some segment. Okay, by some segments. okay, by some segments. For example, this top is contributed by this segment. This bottom is contributed by this segment. So you may wonder, another question you may ask is that, how about the vertical segment? The vertical segment. My answer to you is, there is no vertical segment. Why? Because of the assumption here, the second assumption. Remember, I told you guys, there's no two, okay, for all the endpoints, no two endpoints share the same x coordinate value, right? So, which include the endpoint from the same segment, same line segment. Okay, because like, okay, for the same line, for one line segment, their two endpoints, if their two endpoints cannot have the same x coordinate, then this line segment is impossible to be vertical, right? Okay? So this is like, you know, you don't need to worry about the vertical line segment at this moment, Okay, we are going to cover the vertical line segment later when we relax this assumption, okay? Okay, so let's take the break, okay? When we come back, we are going to discuss a little bit more about the trapezoid property.